I'm Yizheng from Tsinghua University in China. Today, I will introduce a smart ring embedded with an IMU sensor. The ring can sense finger touch on any physical surface, for example, this table or the wall. So in this work, I collaborate with Chun, Zhipeng, Shuchang, Xiaoying, and Yuanchun. Here's the video. The ring senses finger touch by the vibration at the touch moment. The accuracy is around 99%. The method can avoid unintentional touches. Users can also tap with various tapping postures. For example, tapping with the middle fingers or knocking with the knuckle. So we first envision a use scenario to motivate our work. So mixed reality headsets can render user interface on any physical surface. In the future, it is promising for users to interact with any surface with direct finger touch. To sense touch, it is straightforward to use cameras on the mixed reality headset. However, cameras have inherent drawbacks. First, the occlusion problem. Second, the accuracy problem, especially in the depth dimension. For example, the state-of-the-art work explores touch sensing with depth camera of HoloLens. A touch is declared if the distance between the fingertip and the surface descends below 10 millimeters. These methods cause missed touches and unintentional touches, which does not provide a satisfying solution. So to address this problem, we image the combination of the mixed reality headset and a ring embedded with an IMU. The camera on the headset is to detect the finger location and the posture, while the smart ring is to detect the touch moment. We focus on sensing the touch moment and achieve a high accuracy and a low latency. So we are not the first to detect touch by smart ring. However, previous work did not focus on touch contact sensing. They used simple fast-hold methods to sense touch, getting an accuracy of up to 90%. In this paper, we used machine learning to achieve an accuracy of 99%. There are two parts in our work. In the design part, we investigate user preference on the tapping postures and the ring placements. We identify a set of useful tapping postures. Our technique can sense the touch moment of all these postures. For ring placement, users like to wear the ring on the proximal phalanx of their fingers. In the technical part, we find that the SVM-based methods can outperform previous work for touch sensing. To optimize the accuracies, it is the best choice to wear the ring on the proximal phalanx of the index finger and the middle fingers. I will introduce our work in 3 user experiments. In experiment 1A, we collected tapping postures that most users are willing to use in daily life. We first defined a comprehensive set of tapping postures. For each posture, participants perform the posture and then rate them in a questionnaire. We exploit the posture in a 3-dimensional design space. First, which fingers touch the surface. Second, which part of the finger touches the surface, including the fingertip, knuckle, and the fingernail. Third, is the hand in a closed fist position or in an open plan position. So finally, we had 70 types of posture to be evaluated. 20 participants took part in the experiment. They touched with 70 postures on a desk and on a wall, and then waited for each posture through the questionnaire. The questionnaire evaluates each posture on a 7-point Likert scale by 3 scores: the physical and mental ease of performing the posture, the ease of remember the posture, and the willingness to use the posture. And here is the result of the user preference. The left figure shows user preference of all the postures in horizontal and vertical orientations. The red color represents a better user preference. Users prefer to touch with the index, the middle finger, 2 fingers, or 3 fingers. They do not like to touch with the ring finger. And they accept only touching with the finger pad, fingertip, and the knuckle of a finger. So it is not a good idea to design a touch gesture that involves the fingernail. Okay. This figure shows the top 10 tapping posture. The result may help the design of touch interaction in the future. In the technical part of this paper, we also sense the touch effects of all this posture. We conducted experiment 1B to investigate user preference of ring placement. Here is the result. Users prefer to wear the ring on the proximal phalanx of their fingers. They do not like to wear a ring on the distal phalanx of their fingers. Now we step into the technical part. We collected motion data from the smart ring when participants touch with different tapping posture and different ring placement. Based on the motion data, we designed the touch sensing algorithm. Before we look into the details, we have the conclusions. First, available information in the smart ring is rich. Machine learning can largely improve the touch sensing. Second, it is the best choice to wear the ring on these two positions. They optimize the performance of recognition. Third, after a touch, the vibration can transmit to any ring placement within 20 milliseconds. Fast, ring-based touch sensing can be low latency. 12 participants touched on the surface and we collected the motion data. The experiment had 3 independent variables: the surface orientation, the ring placement, and the tapping postures. And we also collect mid-air gesture as negative samples, such as swiping in the air or drawing a circle. This figure shows our apparatus. The participants wore a smart ring and touched on a low-latency touch screen. The IMU ring can collect angular speed, acceleration, and the direction of the gravity. The frequencies was 200 Hz. The touch screen collects the ground truth of the touchdown event. The latency was below 5 milliseconds. We used the lip motion to check the hand. Next, I will introduce the touch sensing algorithm. We have the details in the paper. Here I just present the final algorithm. We first trained a SVM model to classify the tapping moment and the mid-air gestures. The left figure shows an example of the positive samples. The positive samples also include the other tapping posture, like knocking or using other fingers to tap, while the white figure shows an example of the negative sample. And this figure shows the motion data around a touch. The red line represents the ground truth of the touch moment. We sample a time window of 50 milliseconds around the touch moment as positive sample. We sample the time window before the touch moment as negative sample to avoid touch events, to avoid reporting touch events in advance. For each dimensions of the IMU data, we calculate its maximum, minimum, mean, skewness, and kurtosis. We obtain a feature of 45 dimensions and use SVM to train the model. The figure shows the accuracies of the model over ring placement. The red color shows the best ring placement in terms of accuracies. Their accuracies are around 99%. The white figure compares our methods with 2 baselines. The 2 baselines are the fast hold methods based on smart ring, and the optical methods based on camera. The results show that our method is better. The classifier was not enough for sensing touch in one time. First, it might trigger a repeated touch event. Second, the classification accuracies of 99% was not enough to avoid unintentional touches. To address this problem, we packed the classifier into a simple algorithm. First, the algorithm does not report touch events if there has been a contact in the past 15 milliseconds. Second, the algorithm reports touch events only if the classifier detects 2 consecutive frames of touches. And we evaluate the algorithm in the third experiment. In this experiment, we evaluate our algorithm by the piano tile scan. We compared our methods with the camera-based method. In the task, the participants can see his virtual hand in a display. The objective was to tap on the black tiles as they appear from the top of the screen, while avoiding the white. The screen moved manually at the rate which the tiles were touched. Participants touched 100 black tiles. To finish the game, they were asked to touch as fast as possible. And here is the result. Our methods outperformed the camera-based methods in accuracies and completion time. The task in this experiment required participants to touch really quickly. The camera methods could not handle this situation well because sometimes the users did not lift their fingers over the threshold of the camera-based methods, which is 10 millimeters. So the delay of our methods is low and stable, while the delay of the camera methods was not stable. Some participants report that the camera-based methods sometimes even sense the touch in advance. So here is the conclusion. In this paper, we focus on touch effect sensing by IMU ring. We identify usable tapping posture according to user preference. We find that it is the best choice to wear the ring on the proximal phalanx of the index or the middle finger. Our work has some limitations. The major one is that we can only detect touch-down events. It will be valuable to sense touch up in the future, so that more touch gestures such as long press and a swipe can be recognized too. So that is all of my presentation. Thank you for listening. I'm happy to take the question.
Thank you. It was a great talk. I was wondering if you did any experiments on putting the IMU on the wristband and trying to see if you can still detect touch using this method.
Sorry?
Did you do any experiments on putting the IMU on a wristband instead of a ring?
Sorry.
So instead of putting the sensor on the finger, if you put it on the wrist.
Oh, this place? Yeah. This is a good question. At first, I did try to use a watch to sense this, but it is not working. So the vibration of the touch can only transmit to this nine phalanx of the finger, and no matter how soft the user tap the desk, there is a vibration. But sometimes it is the peak of the motion data is high. Sometimes it is low. But the machine learning method can handle it well. But if we use a smartwatch to send it, the motion data is just like random. Sometimes when the user touch really soft. Yeah.
So it's Dan Vogel from the University of Waterloo. So I especially like the study of different type of touch gestures. That's tapping gestures. That's going to be really interesting and really useful. When you did your experiments to understand the accuracy rate, I could imagine many false positives, right? If I tap against my pants, or if I pick up a cup, it's very impressive, 98%. But is that using the type of sort of wiggling the fingers in space as you're not tapping ground truth, or did you use a more diverse set of realistic hand motions and touches?
Thank you. That's a good question. So in our work, the negative samples are the mid-air gesture. We did not collect the gesture, including the collision. Sometimes when the collision occurs, it will be a false positive sample, false positive. So we think that in the field, we can add a button on the ring. When you are not using the ring, you can just turn it off. And when you turn on it, once you don't collect your finger, there will be no false positive. Yes. Thank you.
This is on? Okay, awesome. Thank you for the talk. So some of your motivation was coming from mixed reality input, where people would want to be tapping not only on a table or a hard surface, but also on the body, and potentially softly. Did you test these, and did you only evaluate sort of in the criteria that you collected your test data in, or did you also do some aspects of testing in the wild?
Thank you. So you mean the surface, the barrier surface? Yeah. In this work, I just test the widgets surface, like the desk or the wall, and after the submission, I have tried it on the screen. If you tap on the leg, it also working. Yeah, it is also working. Yeah.
It was actually just exactly the same question. So great talk. Thank you very much.
Yeah.
My question kind of builds on top of that question. What set of data points that you collected in terms of positives and negatives, and how well does it generalize across surfaces?
Sorry.
So how many data points you collected for positives and for negatives, and how well does it generalize across users, or do you need to fine-tune it per user?
Yeah, we have the details in the paper. In the paper, there we describe the negative sample, how we collect the negative sample and the positive sample in details. So maybe we can see the paper. Yeah, the data is not that much. We recruit 12 participants to collect the data. One participant collect the data for 1 hour, and it is enough. Yes.
All right. Let's thank the author.